Hi, my name is Mike Danielchuk, and I'm excited to present our work at NVIDIA's Seattle Robotics Lab on object rearrangement policies that make use of learned collision checkers between partial point cloud observations. When considering a task like the one shown here, where the robot must iteratively grasp, lift, and place objects into a specified zone, the robot must continually try to find a path to its current goal. This motion planning problem, where one must find a sequence of configurations that take the robot from point A to point B, is ubiquitous in robotics. In addition to resulting in the robot reaching its goal, the set of configurations must keep the robot from colliding with itself or colliding with the scene around it. Determining whether each configuration in the scene is collision-free can be quite a computationally expensive process, with some estimates suggesting it can take up to 90% of the total planning time. Thus, there is significant motivation for fast and precise collision checking capabilities. In order to find a collision-free path, previous works commonly use one of three approaches. Model-based collision checking assumes a model of each object is available and determines whether the robot model will collide with each of the object models in the scene using fast analytic methods that compute intersections between triangular meshes. Another approach is to approximate the objects without models via voxelization and check collisions between the robot model and the voxel grid of the scene. A third approach is to compute an approximate sign distance field of the objects in the scene and evaluate the signs of many points sampled from the known robot mesh. When using known mesh models for all objects, the flexible collision library, which leverages well-known algorithms for checking intersections between polygons, is commonly used. Pan, Chitta, and Minocha also introduce a method for checking collisions directly between point clouds and meshes, or between two point clouds, which attempts to find a separating boundary and measures the likelihood of points lying on either side of the boundary to determine whether two objects are colliding. There are benefits and drawbacks to both approaches. Namely, the mesh-to-mesh collision checking methods are very fast and exact, but require accurate mesh models and poses for each object in the scene, while the point cloud methods operate solely based on observations, but can be significantly slower and are not exact. In both cases, there may be inaccuracies in collision detection due to pose estimation errors or due to partially observable point clouds. In our work, we consider the case where mesh models are not available for the objects in the scene, but at the same time strive for the fast computation time of the mesh-to-mesh collision checking methods. To address this objective, we propose SCENECOLLISIONNET, a learned collision checking model trained entirely on simulated partial point cloud data. We show how SCENECOLLISIONNET can be integrated in a model predictive path integral controller to rearrange objects on a tabletop from a single view in both simulation and in physical experiments. We also show that SCENECOLLISIONNET can be more accurate than previous methods when presented with partial point cloud data, and is also significantly faster due to its ability to batch up to 500,000 collision queries in a single forward pass. The inspiration of SCENECOLLISIONNET mainly derives from recent work in learning implicit 3D shape representations, such as deep SDF or local implicit grids. These methods learn a boundary function in 3D that encodes the underlying shape from point cloud inputs. They have shown an incredible ability to closely match underlying surface geometry even in the presence of noise. However, they're not directly applicable to collision detection in robotics, since they typically have slow inference times due to online optimization steps, and they can generalize poorly to unseen object models or classes. In robotics, we want fast inference and very good generalization to unseen objects. Our key insights when designing SCENECOLLISIONNET's architecture were twofold. First, a complete shape representation may actually be more information than we need to predict only collisions between point clouds. And second, scene and object encodings should be able to be reused for collision queries, since the object transformation changes as it moves through a scene, but the scene itself does not necessarily change. The first branch of SCENECOLLISIONNET's architecture encodes a scene represented as a point cloud using a shared multi-layer perceptron, then voxelizes the scene into coarse voxels. Features from neighboring voxels are shared via voxel convolutions, which results in a set of features per scene voxel. This scene encoding only needs to be computed once per scene and can then be reused for all subsequent collision queries. An object point cloud is similarly encoded using PointNet++ set abstraction layers. In a similar way to the scene encoding, the object encoding also only needs to be computed once for a given query object. Then, for each collision query, we can find the voxel that would contain the object center and express the transform with respect to the voxel center. Thus, we can batch all queries from all voxels through the same classifier, which just takes a concatenated vector of voxel features, object features, and a relative transform representing the object within that voxel. By batching queries in this way, we can fit up to 500,000 queries on an NVIDIA 2080 Ti GPU in a single forward pass of the network. To train the network, we generate a dataset of over 1 million scenes with 10 to 20 objects scattered around a table. We then choose an object that travels on 64 linear trajectories across the scene, checking ground truth collisions using FCL at each time step. Here we show the ground truth collisions as the color of the object, with green being no collision and red being collision. Each data point consists of a scene point cloud, an object point cloud, a transformation of the object within the scene, and a collision label from FCL. We train the network on a total of over 2 billion of these collision queries. We benchmark the network against a series of baselines across 1,000 scene object pairs and over 2 million total queries, measuring accuracy, average precision, and time per collision query. Objects in the test scenes are unseen in training. SDF baselines encode the scene or object point cloud as a sign distance function and check the sign of each external point to predict collisions. FCL methods are parallelized across 10 threads and use marching cubes to convert point clouds to meshes before checking collisions using the flexible collision library. Finally, PointNet Grid is an ablation of our method that does not contain any coarse voxel convolutions, so there's no shared information between voxels. Our method achieves higher accuracy than baselines while being 75 times faster than the multi-threaded FCL baseline, which is the next best baseline. We also show an application of SCENECOLLISIONNET as part of a model predictive path integral, or MPPI, controller for object rearrangement in a real-world tabletop setting using a Franka Panda robot and an Intel RealSense camera. In these cases, SCENECOLLISIONNET is used to determine collision-free grasps and placements, as well as collision-free robot trajectories when reaching to grasp or to place. To take advantage of the massive parallelization of SCENECOLLISIONNET, we sample a set of joint space trajectories around a linear trajectory from the current configuration to the goal configuration set, shown here on the left. We then trim each trajectory such that it's collision-free. Each of the robot's links, as well as the object in hand, are checked for collisions along each trajectory. To do this, we transform the robot links and the object in the hand using forward kinematics. Then, we sample points on each link, shown here colorized by the link. Each point cloud of each link then forms a collision query consisting of the link point cloud, the scene point cloud, and the relative transform of the link points within the scene. All of the queries from each trajectory for each link and the object can then be batched together in a single forward pass of the network. Additionally, the object encodings for the robot can be cached ahead of time, so we can further speed up computation since the geometry is previously known for the robot. After trimming, the cost of each trajectory is calculated as the L2 distance in joint space to any of the goals in the goal set, and the lowest cost trajectory is executed. Note that the cost is equivalent for grasping and for placing. The only difference is the goal set configuration. The process then continues at each time step, which allows the policy to adapt to a changing scene. We can also leverage the replanning aspect of this policy to perform reactive grasping when the object to be grasped moves. In addition to reactive grasping, we can also perform reactive placement with moving obstacles, where the moving obstacle forces the policy to choose a new placement location after the first one becomes occupied. We show that the MPPI policy can successfully operate in real-world scenes with noisy point clouds to pick and place objects even among clutter in the placement zone, or when it's required to significantly deviate from the straight line trajectory to the goal. The policy performs very well in real tabletop scenes, but may still collide with the scene occasionally. In future work, we will leverage the continuous nature of our collision predictions to plan more conservative trajectories and also explore new techniques of generating candidate robot trajectories. Supplementary material and full videos of the robot experiments can be found at the link shown here, and our code is available for reproducing SCENECOLLISIONNET training and rolling out the MPPI policy in a simulated environment. Thanks for listening, and I'm happy to take any questions.